to the Breker SoC Verification workshop featuring the Synthesizable VerificationOS. This workshop was a big hit at the recent DVCon 2021 conference. During this workshop, after briefly discussing how SoC verification is evolving, we will feature an interview with Mike Chin, Principal Software Engineer at Intel and a well-known expert at SoC verification, where he will discuss evolving SoC verification requirements that he sees and the industry trends that are driving this. We will then go on to hear from Adnan Hamid, CTO at Breker Verification Systems, where he will provide an in-depth discussion on SoC verification and how this new concept of a synthesizable verification OS may be used. And finally, we'll do a quick summary. So how is SoC verification evolving? Well, in the past, functional verification was often focused at the IP level, and the SoCs were made up of interconnected blocks and required little additional functional verification. However, today, we see a different situation. Modern SoC complexity requires a lot more verification. For example, the infrastructure is far more complex than it used to be. Interconnect, coherency, security are all issues that must be fully verified. Functionality is now spread across multiple blocks and software, and this needs to be verified as a complete unit. The SoC has operations running concurrently, often using the same resources such as memory, specific I/O ports, and so on. And of course, now much of the hardware and software is developed in parallel and must be considered in parallel as well and verified in parallel. So we believe SoC verification requires a new look, and this is the purpose of this workshop. So we would like to welcome Mike Chin, who's a principal software engineer from Intel, in today's workshop. Thanks, Mike, for participating in the workshop today.
Not a problem.
Cool. So firstly, Mike, maybe you could provide the audience with an overview of the kind of work that you're doing today and how you sort of, operate within Intel.
Sure. I'm in charge of validation software for a number of our IP blocks that we have inside of our SoCs. So we look at different things like different types of IP controllers for devices, high-speed I/Os, security, all sorts of different types of usages that you would have within a platform. And we need to validate all of those. And my team and myself, we write the software that we use to do what we call spec level validation of the IP, making sure that everything is working before it gets released out to the customers.
Oh, excellent. Okay. So you're obviously working with a lot of big SoC designs and doing a lot of validation across those.
Yeah, within every SoC, our IPs are we have upwards of 25 different IPs that we're working with to do validation and trying to get everything working at the same time. Both, it's an interesting problem because you look at it from validating the IP, but then you also have to look more broadly outside of just the IP scope, look at it from, say, the SoC itself. Now, we have the IP, you have to eventually integrate into the SoC. And one of the driving factors that we have is to make sure that our ability to shift our content and our validation goes from that IP block all the way to the SoC.
Right.
And so that's been a huge challenge for us because not only are you looking at IP to SoC scalability, but we're also looking at things like platform scalability, going from simulation platforms, emulation platforms, different FPGAs for pre-silicon, all the way to your final post-silicon platform. Wow. This is the type of gamut that we have to cover when we're doing our work.
So, Mike, backing up for a second, we've talked in the past about some of the big industry challenges that are out there, and I think are there for many different companies, right?
Yes.
Would you just like to elaborate on some of those and how they might affect you?
Well, I think the biggest one is the competitive drive that you have within every single company out there, right? And it's really how soon can you hit the market? your TTM, your time to market, has to be as fast as possible for you to be at the bleeding edge of competition, and for you to be at the bleeding edge of technology. And because if you're not at the leadership position, then you have a problem. You're falling behind, and it's hard to catch up.
Yes.
Right? So number one is your time to market, and from there everything comes into play of how do you get there? How do you make this happen? Because being first doesn't necessarily mean you're best.
Right.
First with quality means that you've got a leadership position, right? So we want to be able to release a product that has high quality. So how do we do that with our validation approaches? We need to look at the completeness of our validation, make sure that we have everything per spec is supported. We've hit all of the different corner cases in the design and made sure that everything is working. And then, you know, I think the other part of the TTM, the time to market, is that fast part, right? We just talked about the quality, but how do you do it fast? And how you do it with a cost that is minimized as much as possible. I'll take a look at a simple stepping of a silicon design that we would put out. And I don't think it's surprising just to think that it costs millions of dollars to do a single stepping. You want to minimize the amount of steppings that you have to do at any given point in time. So how do we do that? And that's kind of the concept of shifting left, right? We want to shift left our validation as much into pre-silicon designs, validating all of our corner cases, validating as much as possible. So that way when we get into post-silicon, we really have a methodology of just being able to make sure everything is sanitized, that the full integration to the system is all there. But really, if we're able to shift left the amount of bugs that we find in pre-silicon to pre-silicon, then in post-silicon, we are going to be far cleaner, far fewer steppings, faster time to market, faster time to PRQ, right? And so all of these things, they really do coalesce around that concept, I think, of making sure that we can be in a leadership position, and you lead with quality and you lead with speed.
Yes, very interesting. So basically, time to market, quality, differentiation through complex designs, of course, and development efficiency. All these things come together, and I guess it really all ends up in terms of cost, right?
Yes.
Direct expense, lost opportunity cost, and so on.
Yes, exactly.
Yeah, interesting. Okay, cool. So diving a little bit more deeply, Mike, into this, you've mentioned in the past some of the specific kind of challenges you have in verification and validation in your area. I mean, would you mind, and I know you touched on this a little bit at the beginning in terms of portability, but would you elaborate on some of these a little bit?
It's really the challenges that you have for, I think, for any sort of design house. It is always taking the IP itself and then scaling it out to the SoC. That's one vector of scalability that we have, and one challenge that we have. Another orthogonal vector is looking at your platform scalability, because it's very easy for us to be able to validate, say, an IP on a single FPGA. But you can't use that inside of a larger SoC. So when you look at your content and you need to scale that, you need to scale from a FPGA or from simulation into a larger SoC emulation, and then ultimately to your post-silicon platform.
Right.
Yeah. And so those are really the two starting vectors that we would look at. The others, I think, you start looking at, say, post-silicon validation, really prepping your product for the end market, for your consumers and your customers. You want to do some level of validation with the type of use cases that they would be using. Operating systems are probably the primary way you think about it, because some people run Windows, some people run iOS, some are on Yocto or Linux. Making sure that your your content or your design is working on those platforms, how do we do that in a very scalable way? That's a really big challenge, I think.
And presumably bare metal as well, I guess, Mike, right?
And bare metal too, yes, absolutely. Because I think for the way that we view it here, bare metal is the start of all of your validation, because that's where you take that IP itself and then you start looking at it, right? We're using a bare metal type of approach. Yes.
Right. Mike, the challenge just related to integrating IP into SoCs these days and the verification around that. I mean, what's your view on that?
It can become challenging. It is slightly less challenging if the design is in-house, because you can have a somewhat seamless handoff from your IP team to your SoC team, from IP validation to SoC. But there's a huge challenge if you are a consumer of third-party IPs, say your PHYs, your even digital logic for some of your soft IP controllers. You want to be able to integrate it, and part of the integration task is running that IP, doing its basic operations, and then making sure that everything is running, right?
Yes.
So one of the challenges that we have seen is, how do you minimize the cost of getting content that will run? And how do you minimize the cost of that content? Because your content platform that you're developing on may not be the same as that vendor's. They may be delivering to, say, Debian, but you're running on Intel Next, or you're running on Windows, right? We all have the challenge is there because we don't all talk on the same language. And I think that's the biggest problem that we have. Even in-house, talking to the same language of pre to post and IP to SoC, if we all talk the same language, then we can all run on the same types of platforms, and different operating systems. And that makes it a lot better for us to move with agility.
This leads to a discussion that you and I have had for a while, which is around this idea of a synthesizable VerificationOS, which I guess, one of the objectives would be to try and equalize these different languages that you're all talking, or we're all talking, and bring some standardization into this process. I mean, what's your sort of view on this idea in general?
I think that it is something I see as a need for my company. But as I look at other companies and their ability to work, or if I put myself into the shoes of an IP vendor, it is advantageous for me. And I kind of go back to the same concept of talking the same language.
Yes.
It's advantageous if we all talk on the same language, because then I can deliver something once. You can take it and run with it without having much interaction from myself or much support. So the support costs are low, both on both ends, as a supplier and as a consumer. And it really helps us to fast track our validation, right? And then think about it. If we're able to do all of this and fast track our validation and do this with higher quality, it comes back to that whole message about time to market. Now we can actually move and deliver faster to the market itself.
Yeah, and I guess shift left as well, right? I mean, I know introducing more concurrency too. Interesting. So as SoCs that you're working on evolve, I mean, where are the stress points these days, and where do you see these even getting worse in the future? And how do you think this could help?
The stress points are always going to be on the system itself, the SoC, and I think that the biggest stress point is always going to be something like power management. You look at very complex systems of cross IP behaviors. You look at very complex behaviors within the IPs themselves when they are trying to do any sort of power management states. And these need to be very well understood and very, very well validated. I can't even stress how many bugs we worry about when it comes to power management, because it is such a complex domain. So I think talking the same language and having content that talks that same language helps us to apply more simplification to that very complex problem.
Right.
Because now we're all grounded in terms of how we view the problem or how we want to address that problem. And that helps us to make a very complex problem a little bit easier to deal with and a little bit easier for us to express and validate.
Certainly, yeah. Okay, Mike, do you have any other thoughts or comments you'd like to share with the attendees here today?
Simply that I think VerificationOS is probably the start of where we want to be. We've had a start already in terms of how do we model our work and using portable stimulus as that means of the industry standard for modeling. When we talk about the realization layer of that portable stimulus, and when we talk about how do we have scalability of that intent, from IP to SoC, from one platform to another, from operating system to operating system, I think this is one of the concepts that we need to be looking at, because it really helps us to be able to then validate more fully and validate more completely.
Excellent. Well, Mike, I really want to thank you for your time and your insights today. I think this has been enormously helpful. You know, thank you very much.
Yeah, not a problem.
I would now like to introduce Adnan Hamid, CTO and CEO at Breker Verification Systems. Adnan will dig much more deeply into practical SoC verification and discuss this idea of the Synthesizable VerificationOS and how this may be used. Adnan, Mike mentioned this notion of a Synthesizable VerificationOS, a concept Breker has been working on for a while now. Maybe we could start a little bit with your idea behind this concept and how it relates to SoC verification.
Thank you, Dave. So Mike talked to us about the need for quality and time to market. And he brought us all the way down to do this, we need a left shift, right? We need to be able to write our tests once and reuse them everywhere. And that got us to this idea for Synthesizable VerificationOS. So what's the idea over here? Well, I've been writing tests for a while, and let's start by talking about what we all know how to do. We all know how to program. Under Linux, we are all taught how to do a hello world, and we somehow call printf, and we run a program, and it just works. When we do that printf, a lot has to happen to make that hello world show up in the right place on your screen, right? Something goes to the OS, goes down to the kernel, something puts in the right place with X Windows. That's cool. When you're running a program, somebody takes care of us. It starts up a new process. It runs us when all our resources are ready. It pauses us when they're not. And when we ask for resources like memory, we just call malloc and somebody just gives us some memory and it's all done, right? We're all very used to this. The aha over here really was, hey, when we go to other environments in verification, we're really solving that same problem over and over again. Let's talk about UVM. Okay, in UVM, our printf is a UVM info, no problem. Our processes become UVM sequences, right? We're running lots of sequences on our VIPs, but the resource management and synchronization across them, difficult. If you're talking at SoC level, if you're talking about an IP that has memory, well, we don't really have any memory in UVM. When we go to the SoC level, first let's talk simulation emulation. Just getting a printf going on from a CPU in simulation is a problem, right? We need to do some kind of trick boxing thing. Processes have to be manually managed. Memory has to be manually managed. And then this is also a problem when we're trying to do bare metal diagnostics for post-silicon. So the aha was a little bit, hey, never mind the test content. There's a framework that we need in each of these platforms. They're all trying to do the same thing. Can we come up with a set of APIs that model what an OS would do for us and implement them in a way that we can synthesize the right framework for the right platform?
Interesting. So can we talk in a bit more detail about the Synthesizable VerificationOS and what are the major components that you need in this?
So the idea is this. Let's separate the realization of these test cases from where the test case comes from, right? So one common place that would come from is a portable stimulus model, right? Or it could be just plain old C++, or we could be taking traces from UVM or from some directed test format. It doesn't matter. We write them all to use or call these virtualized OS services. Then we have the virtualized OS deal with the scheduling, the resource management, and then have the synthesis flow generate the right framework for the right platform. Because the fact is, we're going to talk about the 3 separate platforms, but everybody's worlds work a little bit differently, and we need the synthesis chops to be able to handle all of them.
Okay, so I understand what you're saying, Adnan. It seems like we have a lightweight verification operating system type of kernel to run verification that has some pieces of, say, what might be in Linux, but not the big overhead of Linux. Maybe you could talk a bit more about some of these virtualized services, the services and the mapping that's involved.
Absolutely. So what are things we got to be able to do, right? We need portable messages. No matter where we are, we got to be able to do our hello world. We need portable registers. We need to be able to program our registers. Register base addresses will change from environment to environment, but the register offsets will be defined by the IP, so we need to have that flexibility. We need to deal with memory allocation and scheduling. How that works will be very different in different platforms. We got to work with the task scheduling, the actual work scheduling. This is the processes we talked about. We got to deal with transactions, right? Every design has to have some kind of I/O. If it ain't talking to the outside world, it ain't doing anything. And finally, we need to deal with interrupts. So these are 6 common things. This is not everything that the API supports, but here are 6 common things that I think most of our audience can easily relate to. Okay? Now, a lot of these ideas are not so new to us. I've pulled over here a few slides from the PSS tutorial that we did just a little while ago. One slide that Tom presented over there was on how we do scheduling, right? And we talked about these parallel constructs and these schedule constructs and what that means in terms of how we can schedule things, what may be in parallel, what may be in sequence. Well, this is cool. But how do we ensure that we get the same parallelism and the same sequencing on all the different platforms? Furthermore, Tom has this very nice slide where he talks through all the different paths that you could come through in this graph. Well, how do we make sure that all those paths have been covered? In that tutorial, I talked about memory scheduling. Okay, we talked about how we do memory management and how memory management has to play well with the scheduling. For example, if you do 3 operations in series, they can keep reusing the same memory, everything is fine. But if you do the same operations in parallel, you may run out of memory because all those guys are trying to run at the same time and you might not have enough memory to support them all in parallel. So you can't really separate the task scheduling from the memory scheduling. Karthik talked about the register modeling in PSS, and we got to be able to define these registers and write them. But how do we write this register? If I'm going into a UVM environment, I got to come through the UVM RAL layer. If I'm going into an SoC simulation environment, I may well need to generate this into a C program that a processor runs. If I'm using the same registers to program a device in post-silicon, say over PCI Express, well, now I've got to generate the correct PCI Express transactions all from the same programming. So how do we pull that off? Another aspect over here is some of our users we see are coming from the UVM background and they're happy to learn this new declarative language. Many of our users, especially at larger companies, have stakeholders all across the stack, from SoC simulation to system integration all the way to firmware. And really, we are not convincing them that a new language is in the best interest. So for them, we are providing the same solutions in just plain old C++. So we can take the register definitions, perhaps coming from IP exact, spit out a register model in C, and then give them an interface to be able to read and write those register models. This is taken very much from the UVM RAL layer, brought up to PSS in C++. And this gives you a way to set individual fields and modify them before you write them. Another piece that I think is required in PSS is transactions, right? So we got to be able to define TLMs. What we're talking about is transactions that we intend to send to some kind of I/O interface, like PCI Express or the USB side of a USB device, right? There's a register side that's coming from the CPU. I'm talking about the wire side. Okay, so so we can define these register models. We can even spit out the UVM code to tie those register models into UVM. And the use model in C is very straightforward. Again, model based on what we do in UVM today. Okay, so familiar things just being done in plain old C++ instead of UVM. So what did I just talk to you about? We have the whole notion of portable stimuluses talking to us about how we can write models that define the scheduling we need, define the memories we need, the registers we need, and the transactions we need, and so on. Okay, and if we can get all of those requests to come to the same virtualized OS, the same set of APIs, right? The Virtualized OS Services. Then from there, we can go write a synthesis engine that can drive to UVM, to SoC simulation, to post-silicon diagnostics, or frankly, generate those same tests back into Linux, where in this case, things like memory allocation would be replaced by the Linux call.
So that's really, really interesting. And I can definitely see how that could be useful, especially for SoC verification. You also mentioned that the Verification OS will schedule a series of tests and also provide execution management as well. Could you give us a sense, Adnan, of how that actually will work and how that fits in?
Absolutely. So let's say we have a little SoC and we have several use cases, right? We have various IO blocks that can drive through various other IPs to create various scenarios. Let's consider first the case where we have only one thread, okay? We could lay down a first scenario, we can lay down a second scenario, and already we're probably doing more than people can write by hand. And again, think about the fact that we're coming through this graph of scenarios and we are covering different sequences of operations as defined by the graph. Well, let's say instead we have 3 threads available. Well, we can create a scenario, we can interleave, interleave, and pretty quickly we have a dense test case with a lot going on. And what's going on over here, right? So for example, in the schedule, there's no row with 2 purple blocks. The tool is resource aware, where these resource definitions are coming from the model itself. And we ensure that the same resource is not used by 2 threads at the same time. Those arrows are producer-consumer dependencies. We know that the producer must finish before a consumer can start. So all of that is automated in the schedule. And how is that scheduling done on these different environments? Well, that's part of the synthesis engine. Scheduling tasks is not enough. We also have to talk about scheduling memory, okay? So perhaps we have 3 memory regions defined for our design. Maybe region 1 is DDR, region 2 is on-chip RAM, and region 3 is flash. And maybe the tool will decide at generation time that the first scenario uses a buffer in region 1 and a second buffer in region 2. And then as soon as the resources are freed up, the next scenario has a high propensity to reuse some or all of the memory that was just released. Right? The point over here is by scheduling the memory along with the tasks, so we can put a lot of thought into what are interesting addresses to pick, such that we're creating lots of memory collisions. Right? It's well known that random addresses, sequential allocations are not very good for verification. We want heavy reuse of the same addresses to create conflicts. So this is the scheduling part of it. But once we have the schedule, how do we drive it into these various environments, right? There are various things we got to do. We got to manage all these threads. Sometimes some of them are coming from CPUs. Sometimes some of them are coming from VIPs. We got to deal with coverage, both the sequential and temporal coverage. We got to deal with debugs. So how do we do all of this? Well, I'm going to talk to you about 3 flows, right? We'll talk about UVM, we'll talk about SoC simulation, and we'll talk about post-silicon diagnostics. When we're working in UVM, then once the schedule is generated, each thread in the schedule is driving a separate VIP or agent in the UVM. Okay? The UVM environment is free to do its own scoreboarding and its own coverage, but so all the tests are self-checking, so they're scoreboarding at the tool level, and the tool is also measuring what coverage it has achieved. We've put some work into making integration into UVM environments very simple. All that is required of the user is to link in a DPI library and to load some system Verilog code that's generated by the tool. The system Verilog code is generated code I showed you when we were talking about the TLMs that we talked about, right? We said we could define a TLM in C++ and then generate the UVM code to hook it up to simulation. And once we have that, we can simply patch into the existing UVM sequences to get requests from the tool and send responses back. So the point over here is the mechanics of integration to UVM can be made very, very simple. A second flow is SoC simulation, SoC emulation. Over here, now we have CPUs in the loop. We might have multiple CPUs. We might want to put multiple software threads on each CPU. And coming through the Synthesizable VerificationOS, the tool will synthesize a C program. In that C program, it'll synthesize threads for each CPU. It'll generate separate programs for each CPU. And it'll generate all the interlocks between operations across the CPUs using shared memory. So all of that is automated. We're not going to think about it. It's going to schedule our memory for us, initialize the memory for us, and so on. Another problem that we have to deal with in SoC simulation is we got to synchronize what we're driving and checking on the VIPs with what's happening in the embedded processor. And since all those operations were co-scheduled when the test was generated, the tool can create an automated synchronization through this execution engine to make sure that operations of the VIP happen in the right order with respect to what's happening on the CPUs. A third flow is in-circuit emulation, FPGA prototypes, and/or post-silicon diagnostics, right? So these are all things where the DUT now looks very much like the chip is sitting, it's connected to a board and things work as though they're working in real life. In these environments, there's a bring-up board, and the actual device plugged into the board, be it an FPGA, silicon, or some socket running off to a big emulation box. Usually we have JTAG and set up, and we already know how to download and run a program. And also, these boards usually have some kind of a console interface, typically done over a UART, where we know how to do printf on one of the CPUs, and it shows up on a console. So in this flow, we're using we're piggybacking on top of that console interface to interact between what's happening on the board and what's happening in the environment side, right? Because we're still open to this problem. How do we synchronize what's happening on the various interfaces with what's happening on the embedded processor?
So, wow, this certainly a very powerful system that can obviously map right across the verification flow. As we move up our V model that we've been discussing, Adnan, maybe you could give us a sense, now we've got a notion of this Synthesizable VerificationOS, how exactly this helps with SoC verification. What are the critical aspects of SoC verification that we need to be concerned about these days?
So what are our verification problems? Right. First, we want to define what needs verifying based on our specs, right? What is verification at the highest level? We've got to prove that an implementation, RTL, matches an intent. Well, today we capture that intent in a whole bunch of different places. We write some of the models in UVM sequences, some of part of the models in C, something in diagnostics. They're all over the place. The same things are rewritten over and over again. We absolutely need a way to move up our level of abstraction. Right? Today, the way we define our verification intent, it's connected right into the implementation of the test. It's just like when there was a time when we did design, our intent was defined right in our netlist, in our gate schematics, right? The implementation and the intent was all kind of one thing. We want to be able to move up. Today in RTL, we just write block level logic, synthesize it, it's done. We can compose multiple blocks to create a system, synthesize it, it's done. We need to come up the same path with test generation. So the first thing we need is an abstracted view of how we capture this intent. We've got to be able to capture intent for individual IPs, and then we have to be able to compose those intents into system-level scenarios. We need to be able to handle this with multiple languages, right? We have to be able to do the declarative portable stimulus standard language that Accelera has defined. For the higher level folks who are working at SoC, system integration, firmware, and so on, they want to be programming in C++, doesn't matter. We got to bring these models in. We got to be able to compose them however they're written. Once we have the model, what this model is telling us is it describes a verification search space that intent covers. Okay, and now we got to go create a way to ensure that they are covered properly. And we're gonna talk about 3 dimensions of coverage today. The notion of combinatorial coverage is well understood, right? System Verilog gives us combinatorial coverage. At a given instance for a given event, we can say, hey, did we see a combination of things? But really, we're asking for 2 more levels of coverage today. One is sequential coverage. We've got to the point where we can reason about, hey, if I have these scheduling operations, parallel operations, I can draw this graph of different scenarios. But now I want to know that I have covered every path through those graphs, right? That I've covered all those use cases. So that's sequential. And then I also want to know that I've done all those operations concurrently. So I need a measure of concurrency coverage. So these are the three dimensions of coverage, right? The combinatorial, the sequential, and the temporal. And the third thing that Mike talked about is we need to shift left, right? So we want to write these models once, and we want to reuse them many, many times. So that really was the point addressed by the Synthesizable VerificationOS. Let's separate how we come up with the scenarios from how we actually run the scenarios, have all the scenarios come to the same common API, and then write the synthesis engine that can go generate the right test case for the right platform. That way, we can write the spec-driven abstraction for the IPs early on when we're developing the IPs, and then we can reuse them up the food chain as we go to subsystem system emulation post-silicon. And then we should be able to compose those IP models into system models and generate system scenarios. So this is kind of the 3 big things we're after, right? Give people a better way to define their intent. We'll create a deterministic way to cover not only combinatorial coverage, but sequential coverage and temporal coverage, and do this in a way that we can shift left, where we can define the models early and reuse them across the flow. So the ideas we're talking about are really not new. And anybody who's at this conference, we all know logic synthesis. And the idea is doing what we've done with logic synthesis for test suite synthesis. Isn't it interesting that in the industry we have DVCon, a conference dedicated to verification, but how come there's no RTLCon, right? Why don't we have a conference dedicated to how we write and reuse RTL? Because we figured it out, right? About 30 years ago, Synopsys came up with this idea of logic synthesis, and that's what drives our industry. Well, this is doing the same strategy, but now for verification content, right? Where we want to write our intent at a high level to create this graph-based model, and then feed it through a synthesis engine to drive all these platforms. So the synthesis gives us the reuse, right? Which is already a big lever in getting our left shift, but we're not done. We need quality. So what do we do about quality? Today, quality means coverage. We kind of know that, okay. Today we have mechanics to measure combinatorial coverage. In System Verilog, we have functional coverage. We can say on this event or at this clock, tell me whether you've seen state machine A be in state 1 while state machine B was in state 5. That's great. It's a beautiful thing. We use it. We know when it's not complete, but it's not enough. With combinatorial coverage, it is very difficult to ask the question, hey, have I seen a scenario where data came in from my modem, it was decoded by my crypto block, and then sent to video? Right? This is a sequence of operations that happen across time, and combinatorial coverage is not real good for that, right? But this needs measuring. Even that is not enough for us. We want to ask, hey, while I was doing the data coming in from my modem, decrypted and sent to my video, have I also been listening to music on an MP3, which maybe something came off an SD card, went through my audio subsystem, and went to the speakers? So I want to know about the concurrency cases, right? A big example of concurrency cases is power management. Have I seen 2 of my big power domains power up at the same time? Because I want to make sure my design doesn't brown out when everything tries to come up at the same time. So combinatorial coverage, not new to us, right? System Verilog does it today. We have tools that can measure it. Sequential coverage is simply taking the graphs that we're talking about in the portable stimulus models, unrolling the graphs into trees, talking about which of those paths are reachable, of the ones that are reachable, which ones have been covered, right? So you can create a nice hotspot graph to a heat map to tell us what is hit, what is not hit. And when you have this much analysis information, very easy to put the tool into automated coverage closure to go cover the paths that have not been covered as yet. Caveat, the total number of paths might be extremely big, so we might have to come along and define which decisions are important to us so we can get a tractable problem, but the math is all there. Once you solve sequential coverage, then you say, hey, have I run all the sequences against each other with all possible concurrency cases? And that gets you to your temporal coverage, where we're wanting to back annotate the schedule with actual observed times to see how things progressed, and then do scripted analysis on it to see, hey, how have I seen all possible overlaps between all possible operations? So, and all of that together lets us do this big left shift, right? So it lets us define our models at an abstract level. We build them at the IP level, start verifying our IPs, combine the IP models to create system models. And as soon as we have the models, we can synthesize test cases for whatever platform is available at that stage in the design. Early on, maybe we have System C virtual platforms. Then we'll go to UVM, sort out the IP blocks. Then maybe we'll go to simulation acceleration to do our subsystems. Eventually, we'll go to in-circuit emulation and post-silicon. And we built the models way back when the IPs were coming up, right? So the rest of this flow is complete reuse, everything driving quality and time to market.
So Adnan, at the beginning of the workshop, Mike talked about the challenges of verification and the industry trends that he sees. Maybe you can give us a sense of the Verification OS, how this applies SoC verification, and how this affects the return on investment in the business of semiconductor development, say.
So what did Mike really talk about, right? What Mike talked about is what each of us have to worry every day, right? Every business, every industry. But especially in semiconductors, where everybody's competing for the same sockets, right? So what do we really care about? We care about time to market with high quality. I mean, there's kind of motherhood apple pie, basically, right? Any CEO of any chip company, sir, do you care about time to market and quality? Yes. Okay, so what does that mean? How do we get this? Well, a piece of it is reuse, right? We better not be reinterpreting our specs over and over again. So the whole idea over here that we just talked about, we started at the bottom of the V model with the Synthesizable OS. What that takes out is one big problem. We can worry about defining our intent and leave some tool to figure out how to run that intent on different platforms. Okay, so that's the lowest level. That raises the possibility that we can write these models early when we are choosing and testing out our IPs, and reuse them as we go through subsystem and system testing, so pushing left shift. Right? As these systems become bigger, we tend to move across different verification engines, going from simulation to emulation to post-silicon. Well, we just use the synthesis tools to go synthesize the right test case for each of these platforms. And eventually we come to silicon, we synthesize in those diagnostics, and everything is set up so that we can drive our time to market. And what am I talking about, right? If you look at where we're spending our time, what stops us from turning out our chips inside a month, right? What drives that time to market? Well, we've known forever from our Wilson studies that we do every couple of years, right? That developing the design, 30% of our time and budget, verifying it, 70% of the time and budget. Well, when we drill into that, we see that about 30% of the verification, right? 30% of the 70%, 30% of the overall budget is developing test content. And why does it take so long? Because we keep redeveloping the same test cases over and over again at different platform levels. We see 25% in debug, where most of the debug is debugging the test cases. So that's 55% of our time to market that can be optimized. And simply by raising the level of abstraction on how we define our intent, and by creating synthesis engines that can synthesize that intent to all our different engines, we can crack that time to market problem and create massive ROI, right? We replace human time with technology, just like we do. We've replaced drawing schematics with logic synthesis. We're going to replace test writing with test case synthesis.
Adnan, thank you very much for this fascinating presentation.
Thank you for having me, Dave.
So to summarize, we've seen how SoC verification is evolving, and we've heard from Mike Chin about the issues and the problems that he sees with modern SoC verification and how this relates to industry issues. Mike's interview was answered by Adnan Hamid, who talked a lot about practical SoC verification and how this idea of the Synthesizable VerificationOS might be used to solve many of these verification issues. Thank you for listening to today's workshop. For further information, please feel free to visit the brekersystems.com website or email us at info@brekersystems.com. Thank you very much.